Anti-patterns. So what is anti-pattern? So the definition I found mentioned in more than one place, one post, one article, was this one, coming from a man that his name is Andrew Koenig. He coined the term anti-pattern in a paper he wrote. And here I place the link for that paper if you are interested in reading that paper. And according to that paper, according to Andrew Koenig, the definition for anti-pattern is just as any other pattern, except that instead of solution, it gives us something that looks superficially like a solution, but is not one. So anti-pattern, it is a pattern, meaning that you can find a specific anti-pattern repeats itself, and in each time the form will be a bit different, but still we shall feel the pattern itself. It is a pattern, just as a design pattern, only that this pattern, it might look as a solution, but it isn't a solution for the problem that exists or doesn't exist. It is not a solution. It is something that looks like, but is not. And usually it comes with a price. Usually it comes with some sort of damage to the code itself. So if we think about the types of anti-patterns, and according to papers I found on the web, we can, for instance, talk about three different categories, three types. So there are anti-patterns in the programming itself, in the coding itself the code itself we code or others. There are anti-patterns in the methodological phase, and there are anti-patterns we can identify in the testing phase. Well, I believe you can find more categories, but these are the three categories I found when digging the web and looking for resources in order to understand what anti-pattern is, what is it, what is the meaning of the term anti-pattern. So let's start with programming anti-patterns. So programming anti-patterns are common mistakes or poor practices when writing code, and they might lead to increased complexity, problems and difficulties with the maintainability, so they come with a price. For example, there is a well-known anti-pattern named with spaghetti code. Spaghetti code is an anti-pattern, a well-known anti-pattern. Those of you who are familiar with PHP, for example, PHP a long time ago wasn't an object-oriented programming language. It became an object-oriented programming language it happened 18 years ago in 2005, but before that it was a procedural programming language. And even when it became an object-oriented programming language, many programmers still continue to write their code without using what the benefits of object-oriented programming. And as a result, we could find open source projects in PHP with lots of code, endless number of lines, something that is very difficult to maintain. So this practice of writing a spaghetti code, we can still see that when dealing with code written by developers that maybe they're not exactly developers, their main job is something else, but they chose to use Python, for instance, for doing some research, and they start writing code that looks like a spaghetti. At first, it's in the beginning, it doesn't look very bad because the program is small, but then it becomes bigger and bigger, and then we get a spaghetti code. So spaghetti code is a well-known anti-pattern in the programming domain. Another anti-pattern in the programming domain is known as lava flow. We're having code that includes lots of code that we no longer need. We saw that happen, for instance, a long time, years ago, when using the Windows operation system and moving from one version to another version just in order to support all programs. The operation system became bigger and bigger, and it included lots of code that probably some of it wasn't really needed, but no one touched it. And maybe you know that you have a system includes lots of code, and some of the code was written by developers that are no longer with you in the company you work for, and no one touch it. People say, don't touch it. It works, don't touch it. And as a result, we get more and more code that is not actually needed. And as a result, the entire system is more difficult to maintain. So it comes with a price. Another anti-pattern in the programming anti-pattern category is accidental complexity. Well, sometimes the code you need to write in order to solve a specific problem can be very simple. There is no need in implementing various design patterns, inventing new classes. There is no need for that. But you're not aware of the mistake you are doing, and you insist on implementing various design patterns, and the code becomes more complex. More complex, it means more difficult to maintain. More complex means that maybe you will have performance problems. I can share with you a case I had in which it happened 20 years ago in my company. We developed a game for mobile telephones. At that time, we were using Java Micro Edition, J2ME, and one of the developers was responsible for developing a space invasion game, and he wanted to show off how well he is familiar with various design patterns. He implemented in the code so many design patterns, so many classes, that eventually the code was too heavy for the device. The game, the performance was very bad. So if you don't need that complexity, don't use it. There is a price coming with that complexity. On the other hand, depends on the programming language you are using. If you use Java or another programming language that supports interfaces, then the minimum, the separation between interface and the class, this is something that I recommend to stick with. It isn't a huge complexity to deal with, but separating into more and more classes, don't do it automatically. Wait a moment. Think about what you are doing. And sometimes the answer is not black and white. And you might get into some conflicts with other developers regarding your thoughts. But the bottom line, if you write code that is too complex, there is a price coming with that. It will be more difficult to maintain. Maybe the code won't perform well, as it happened in my case. So pay attention. Hard-coded. Well, in the program we develop, sometimes we need to use settings, values, numbers, and addresses, kind of a list of values that we can treat as settings for the application we develop. And when this is the case, separate those numbers and addresses and text, take them out from the program. Have a separate file. Don't hard code those addresses, URL addresses, IP addresses, numbers and so on in the code itself. It would be simpler for everyone if that list of values won't be embedded in the code itself. It would be simpler for everyone if it will be stored separately in a file, in a separate file or database. So it would be simpler in the future to modify those values. We will just need to go to that file, that configuration file we decided to have, and change the values. That's all. But if you don't separate, if you don't take out those values from the code itself, it will be more difficult to maintain the project in the long run. So hard-coded, this is another anti-pattern in the programming anti-pattern category. The God object. Well, there is a very important principle known as single responsibility principle. It is one of the 5 most known principles in software development, in object-oriented software development. And I mean Solid. If you're not familiar with Solid, Google and you will find SRP. It is the first principle. And that principle is very simple. It is about having each and every object responsible for a specific task or specific something specific. Each and every class is defined for a specific reason. And the moment we include in our class code that is not related to the target for which the class was created in the beginning, we violate the single responsibility principle. And the anti-pattern I'm talking about is known as the God object. It happens when a programmer define a class and that class is instantiated, and there is an object that handles too many responsibilities instead of to be focused on the responsibility for which the class was defined. Instead of having one object that is responsible for so many responsibilities, separate that object to few separated objects, which means that we will have separated classes, and that way we won't violate the single responsibility principle, but more important, we shall get a program that is simpler to maintain in the long run. So for instance, if you define the class car and an object instantiated from the class car is responsible for the car in general, and then there are various methods you can invoke on that object in order to perform things related to the engine itself. And later, there are various methods you can invoke on that object in order to do stuff related to the wheels or to the light and so on. This is not good. This is an indication for having the God object anti-pattern. Stop. Instead of having one class, the car class, separate that definition of that class into separated classes. You can define the class car, you can define the class engine, you can define the class light, the class wheel, and so on. And then when calling a method for doing something, it would be about calling that method on the specific object that is responsible for what the method is related to. So if it is about change something in the engine, it would be calling a method on the engine object, the object that was instantiated from the engine class. So be careful of having one object responsible for too many things. We better have separated object. Each object is responsible for something. This way we get code that is simpler to maintain. The next anti-pattern in the programming anti-patterns category is the magic numbers. Well, when having number hard-coded into our code, instead of defining a constant that holding that number and then using that constant, then we can say it is an indication for having the magic number anti-pattern. Or when having a constant that holds a specific number, and that number is important, we use it in our code, and then somewhere in our code, instead of using the constant, we use the number. This is an indication for the magic number anti-pattern. And I can share with you a small story. It was 22 years ago when the J2ME technology emerged. J2ME stands for Java 2 Micro Edition. It is a version of Java that you could find on mobile telephones, and you could develop games and applications for those mobile telephones. I'm talking about those mobile telephones we had before the emergence of iPhone in 2007 and before Android, of course. So at that time, we developed games and application, and I can still remember one of the developers two developers were working on a game for a specific mobile telephone, and it was a very impressive game because you found yourself fighting against a dragon and so on. And it works excellent on their mobile telephone. It didn't work on my mobile telephone. It was the same device, the same model. I can still recall it. It was Motorola i85S. Listen, the same device. We bought it at that time. No, they gave us. We didn't buy it. Maybe you remember the company Mears. It was the first company in Israel that gave mobile telephones with J2ME, and they sold games and applications, and we developed lots of games and applications for them. And the same device coming from the same company, the same model. On one device, the game worked fine. On the other device, it didn't work. And it was very difficult at that time to find the reason, because we couldn't debug the game on the device itself. There wasn't, that option didn't exist at that time. And then finally, after a few days, we found the reason. The code of that game was using a specific constant that was defined as part of the J2ME API. Now, the developer, instead of using the constant, chose to hard code the value of that constant. Now, the difference between the two devices that we had was that one of the devices had a newer software version, meaning that the entire software on the device itself, including J2ME, the JVM, the API, the classes, and so on, was of a newer with a different version comparing with the other device. The moment the developer chose to use the value itself, the number itself, instead of using the constant, and the constant was part of the API, we had a problem, because one of the devices was with a newer software version, and for some reason, those developers of J2ME chose to change the value of that constant. And as a result, the game worked fine on one device, didn't work on another. Well, at that time, the term anti-pattern, of course, wasn't known for. I didn't know about such a thing. And magic numbers, this is the name of the anti-pattern that we add in that game. Yeah, it didn't end well, but as of that moment and on, we made sure we paid attention that we use the constants and never use the values of those constants, just to be on the safe side. So if the value of the constant change for some reason, our program will continue to work because we use the constant, not the value of that constant. Okay, then. Now let's move forward to another category of anti-patterns known as methodological anti-patterns. So the first is premature optimization. Well, as you probably know, we live in the year 2023, and it's not new for some years. The main cost, in most cases, the main cost is the developers' salaries. This is the main cost when developing a new program, the salaries. Now, doing an optimization for our code, explore various possibilities in order to choose the one that works the best, in most cases is not necessary. The computers are fast enough in most cases. So we better write our code, do it well, do it the fastest possible, move forward, and don't stop with various research, asking ourselves how to optimize our code, because in most cases, it would be a waste of time. It will generate additional costs. And it even might lead us to unnecessary complex code, which is more difficult to maintain. The best would be to wait with the optimization if needed, because most likely it won't be needed. But if needed, let's wait with it to the end of the development process, not in the beginning. It is a waste of time. It generates unnecessary cost. We don't need it. So premature optimization is one anti-pattern. Reinventing the wheel. Well, if you need a solution and that solution already exists, most likely that the solution that already exists is the one that you should use, especially if it exists as part of the API, the official API you use when coding your project, official Java API, official C#, MSDN API, and so on. No need to invent something that already exists. You need a linked list. In Java, you have a class, its name is linked list. Check the possibility to use it. Most likely, it will work fine and will provide you the linked list you need. Don't invent a new linked list. It is a waste of time, meaning additional costs. And in addition, most likely that the solution you will develop, if you insist on developing your own linked list, won't be as good as the one that was already developed and tested. And I'm not talking about the testing that you might want to conduct, and they won't match the testing that were already done with the solution that already exists. So reinventing the wheel, pay attention. If there is something that was already developed for us, use it. Don't reinvent the wheel. Don't insist on developing something of your own, because it is most likely it would be a waste of time. Most likely you won't get a solution as good as the one that already exists. Probably the solution that you will develop won't be tested as the solution that already exists was already tested. So pay attention, don't reinvent the wheel. The next anti-pattern, copy and paste. Well, this is a practice many developers are used to. They take code from one place and copy and paste it to another. Well, the result, I don't say don't take code that already exists. I just say refactor the code so that you can reuse it. For instance, if there is a utility you need and that utility was already coded in another project, you can take that code from other project and refactor it and place it as a static method or in a specific class or something like that, and then reuse it. So you can reuse it again and again. Don't just take the code and just copy paste it. Because if you are just copy paste and you don't look into the code itself, in the long run, we shall have unnecessary code. In the long run, it will be more difficult to maintain the code because we shall have code that we don't understand, and we won't be able to reuse the code. So if you took a decision to take a code from another project, go over the code you took and reorganize it, refactor it, make it suitable for what you need. And then it would be more simpler. It would be simpler to reuse it. It would be, the code we get will be simpler to maintain if you take that code, refactor it, maybe put it in a method, a new method you define in order to use that code. But don't just copy paste, because if you copy paste code, you get redundant code, you get a project that is more difficult to maintain. Be careful of that. And now to the third category, testing, software testing anti-patterns. So the first anti-pattern is when testing one thing with a framework or a library that was developed for another type of test. For instance, we have different types of tests. For instance, performance test. In order to test the performance, in order to see how the project works when we have extremely high traffic, huge data, and so on. You can't just take a library like JUnit, library we use for unit test, and use it. JUnit is a library for unit test. It is not a library for performance test. There are other libraries for performance test. Take the library suitable for the type of test you conduct. For instance, if we deal with Java, then we have JMeter. When taking the right library, probably the test will be a better test. It will the thing we want to test will be tested. So wrong kind of test. This is one anti-pattern we can see in the testing phase. Another anti-pattern, when writing a test, make an effort to test the external behavior of the component without getting into the internal state of the component you test. Because if you get into the internal state of the component and test it, whenever the system change, whenever the product change, we will need to change the test itself. We better stick with the behavior of the component, the external behavior, without getting into the internal state itself. And I believe this is the last anti-pattern, the happy path. When coding tests, be careful of tests that focus on the most common and expected cases. Try to test the unexpected. Try to test cases that are not common. Only then you will have proper tests. If you stick with the main, most common expected cases, then this is an indication for the happy path anti-pattern. And yes, that's it. As promised, 29 minutes. Okay, questions, please. Okay, then. So thank you for joining the meetup. I wish you all the best. And as promised, I will send you a follow-up message through the Meetup platform with the video and the slides. And have a great day. Bye-bye. Okay. There is a question, random test and property-based test in TypeScript. In Java, we don't have objects in Java are not, we don't have in Java we don't have properties, not in the meaning of the classic properties as in C#, Scala, Kotlin, and so on. And we don't, and when dealing with objects, an object is not a collection of properties. So talking about property-based test, if this is what you meant, we don't have it in Java. Random test, this is something I'm not familiar with, random tests. Internal implementation, no, we don't want to test the internal implementation. If you're dealing with a unit test, this is something else. You test each and every method separately. This is one thing. If you are dealing with testing, let's say we mentioned functional test, for example. Functional testing that a component does what is expected to do. So if there is a component, an object that represents, let's say, a chat, for example, something you can chat with, test that it works as expected. You can write a test that works as an imaginary user that interact with the chat and enter some text, press send, and then we expect to see that text coming back. And we can write tests with more users and see that it works as expected. When doing so, we test the external behavior of the component. We don't test the internal implementation. We don't care about the internal implementation when testing functional, when conducting functional tests. So, but if you choose in the domain of functional testing to test exactly what happens inside the component itself, then it is wrong, because then if something changes in the long run in the way the chat is implemented, then you need to update your test, otherwise the test fails. And this is something we want to avoid, so we better stick with the exterior of the component without getting inside. We get inside and test the method in another type of test, unit test. Unit test is a low level test. For each and every method, we write a specific test. If we have good tests for those methods in each and every class, and then pressing the button, all tests are executed, we shall get green light if we are okay. This is this is about low-level tests, unit tests, but there are higher level of tests for like functional tests. When testing a component, then test the external behavior. Don't do something that tests the internal in this when testing the functionality of what you developed. This is the meaning of what I mentioned before. Maxime, is that okay?
Can I give you an example? In my application, I have a converter for values from pounds to kilos, from ounces to liters, and so on. This is never called from the external user. Should I test this?
It sounds like a very simple application. A converter, it is something in JavaScript.
The converter is a part of application.
Part of application.
Very internal part. dedicated testing of converters, a case of internal implementation tests?
No, in that case, so you have a big application, and the converter is part of that big application, and the converter is actually a class with methods. Is that correct?
Well, yes.
So you can write unit tests and write those methods one by one. This is what we call low-level testing, just to be sure that each one of these methods work fine and does its work, does what it needs to do. So you can test those methods one by one, and we shall call it a low-level test. It is a unit test. This type of testing is known as unit tests. But when you test the whole application, I don't know what that application does, but I believe it allows the user to do various things. Then when testing those various things, and you know, there are frameworks that allow you to set up an imaginary user that interact with your entire application. Then we test the outer scope of the component. We test the result. We don't care about what happens behind the theme in those tests. Usually it won't happen because the frameworks we are using these days usually allow us to set up an imaginary user, and that imaginary user interact with the system, with the application, and then we test the functionality of the system. We test in order to verify that it works as expected. And when using those frameworks, we won't find ourselves interact with the internal state, with what happens behind. So we are in a good place. We won't have a problem. We won't find ourselves testing the internal implementation. But it's not always the case. Sometimes we develop a huge library without user interface. It is kind of a framework maybe. And then we have lots of classes, and we have the low-level tests, which are the unit tests we develop for each and every method in each and every class. And then we also have what we call the functional testing, which is something else. And when doing that functional testing, let's avoid the internal implementation. Let's treat the application as a black box, as a component. And let's focus on the way that component works, if it provides what we expect or not. But let's avoid the internal state, because if you happen to check something that relates to the internal state, and after a while someone changed the code, then you need to update your test, and that causes lots of headache and a waste of time, because sometimes you don't even know that you need to go and update your test. The test fails, and you don't know why, and you think the test is fine, but actually there isn't any problem. The test failed because it refers internal state that was changed. That was the reason. So you see, you find yourself in a scenario where you are doing your work fine, you wrote a test, you're absolutely sure the test is fine, but the test, just because it referred something in the behind, something that relates to the internal state behind, and something in the code changed, now the test fails. The test fails not because we have a problem, it fails because someone changed the code. You see the scenario?
Yeah, thank you. That makes sense.
Just think about systems and projects. Not every project has a user interface. When the project has a user interface, then the functionality testing, you do it with a framework that allows you to set up an imaginary user, and then the test doesn't interact with the internal implementation. But when this isn't the case, when you develop a library, for instance, a library that doesn't have any user interface, then the functional testing, you must be very careful to test the external behavior of each and every component you test, not the implementation, not the way it is performed behind. the code behind. Oh, do you get me?
Yes, it makes sense.
Okay, great. Okay, so if you don't have any questions, so that's it. I will send you a follow-up message, and thank you for joining the meetup. Good luck. Bye-bye.
Thank you.
You're
Bye.
welcome. Bye-bye.